Ask My Instructor 4.2.75. A typical population curve is shown in this slide. The population is small at t equals 0 and increases toward a steady state level called the carrying capacity. The population of a species is given by this function where t is measured in years and where both k and b are positive real numbers. If k equals 250 and b equals 51, find the carrying capacity or the steady state of the population. The carrying capacity is just the horizontal asymptote as t increases. So we're looking for the limit as t goes to infinity of p of t. I divide the top and the bottom by t squared, and that allows me to take the limit because 51 over t squared is going to 0, and 250 just stays at 250 and 1 just stays at 1. So when the separate limits exist, then the limit of the quotient and the limit of the sum exist as well. So I have each one of those pieces, the limit exists, and so to find the limit I can just find the limit of the pieces and do the arithmetic. So the carrying capacity of the population is 250. But notice that 250 is what we set k equal to. So we can make a general statement that the population has carrying capacity k. So when you have p of t equals kt squared over t squared plus b, the k will tell you the steady state or the carrying capacity. When does the maximum growth rate occur? Now, growth rate refers to p prime. It's a little bit easier to think in terms of distance and velocity. So if your function is distance, then the derivative is velocity. Now this time our function is population, and so p prime is growth rate. As time increases, what happens to the population? So what we're looking for in terms of growth rate is p prime. And we're looking for the value of t where p prime is the greatest. Keep in mind that p prime is a new function. So p is population, that's a function of time. P prime, that's the growth rate, that's a function of time as well. So what we'd like to do now is find p prime. And you can see that to do that, you're going to need the quotient rule. So set up the quotient rule. It's the second times the derivative of the first minus the first times the derivative of the second, all over the second squared. Find the derivative of the pieces, and then just start working on the algebra. And we get this for p prime. Again, p prime is a function. In fact, it is the growth rate function, telling the growth rate of the population at time t. Just like with a distance velocity, at time t, the first derivative tells you what's your velocity at that time t. It's the same idea, but this time it's growth rate. What's the growth rate at time t? In order to find the maximum of p prime, we can use the first derivative test. So, so what we're doing is we're finding the first derivative of p prime, which is the second derivative of p. So what we're going to do next is find the derivative of the growth rate function. As I said, the derivative of the growth rate function, that's the idea there would be acceleration. So we're looking for p double prime, which is the derivative of p prime. And again, we have to use the quotient rule. The second times the derivative of the first minus the first times the derivative of the second, all over the second squared. Now you're going to have to operate very carefully. It's going to be, anytime you use the quotient rule, you need to be careful. So just go very carefully, clean up the algebra. I'm going to divide the numerator and denominator by t squared plus 51, and I'm also going to factor out the 25500. And when I do that, it makes the numerator much more manageable. And this is what I get for p double prime. Now, what happens, I simplified the piece in the orange frame, and then I got the bottom line. When does p double prime equal 0? Well, that's going to equal 0 exactly when the numerator equals 0, which occurs when 51 minus 3t squared is 0, or t is equal to the square root of 17. So the maximum growth rate occurs at, remember t is years, the square root of 17, which is a little more than 4 years. That's when the maximum growth rate of this population will occur. Now the thing I want you to notice is that 51 was what b equals, and the maximum growth rate occurred at 51 divided by 3, taking the positive square root of that. So if I were to make a generality, I would say the maximum growth rate of the population occurs at the square root of b divided by 3, and then if you clean that up, you'd have the square root of 3b all over 3. So looking at the graph, I have my carrying capacity is k, and the inflection point, or the point at which the maximum growth rate occurs, is at time square root of 3b all over 3.